Afternoon. So we start today dissertation defense meeting. First of all, I will introduce with the dissertation defense board, which was approved by the Vice Rector of Innovations and Research of Kaunas University of Technology on 2023 month May and the day 29 by decree number PP 667. So, Professor Arvaidas Galdikas, Kaunas University of Technology, Technological Sciences, Materials Engineering, Chairperson, it's me. Professor Dr. Nalin Dugarian, Yerevan State University, Natural Science, Chemistry. Yes, we have. Professor Saulis Grigalevičius, Kaunas University, Kaunas University of Technology, Technological Science, he is online, you can see, and Professor Valery Yashchuk, Taras Shevchenko, National University of Kiev, Natural Sciences and Physics, also online. Yes, we hear. And Professor Yelita Ostrovskaite, Kaunas University of Technology, Technological Sciences, Materials Engineering. So all the board members participate in our meeting. So we have dissertation work prepared by Roni Sebastian Bernard and supervisors was two, as I understand. First supervisor was Dr. Valeria Levichine, and the second supervisor, no, what it is?
Temporary supervisor.
Temporary supervisor, Professor Jozas Grigalevičius, and also Jozas Grigalevičius is advisor of this board. So what I need to introduce, now I introduced everything that was necessary. Now we will ask to present his dissertation. We will ask Roni Sebastian Bernard. Dissertation title is written. I don't need to read again. And please, you have 20-25 minutes to present your main results, ideas, and concepts. So please.
Thank you all. Welcome. My name is Bernard Roni Sebastian. My scientific supervisor is Dr. Victoria Levichine, and my scientific advisor is Professor Grigalevičius. Today, I would like to present my doctoral thesis entitled Synthesis and Investigation of Electroactive triphenylethene, carbazole, and triphenylamine derivatives for organic light-emitting devices. The aim of the work is to design, synthesize, and investigation of new organic electroactive compounds for applications in organic light-emitting diodes. To achieve the aim, the following tasks were formulated: synthesis of triphenylethylene-based compounds, based trifluoro-methylphenyl disubstituted aromatic diamines, methoxy-substituted carbazole-based polymers, and V-shaped carbazole-based derivatives with various donor moieties. Investigation and analysis of the properties of the synthesized compounds, study of compounds as whole transporting materials, emitters or hosts for fluorescent and phosphorescent organic light-emitting diodes. I'm sorry, the pointer doesn't work on the screen, so. A small introduction on an organic light-emitting diode. A device is typically composed of several layers of thin films with organic materials sandwiched between two electrodes. When electricity is passed through the electrodes, the charge carriers through the organic layers and recombines at emissive zone, giving us electroluminescence. The materials synthesized in this thesis were used as organic materials for such devices. The first series of materials is based on triphenylethylene compounds. The target materials 1 to 4 were synthesized in two-step synthesis process. In the first step, for compounds 1 and 3, Buchwald-Hartwig reaction was used to acquire the intermediates, and for compounds 2 and 4, nucleophilic aromatic substitution reaction was used to acquire the intermediates, and in the final step, Hay coupling was used to acquire all the target compounds. The structures were confirmed by NMR spectra as well as single crystal measurements, and for compound 2, we can see that as unusual cyclopalladiation was observed, and this was confirmed by single crystal analysis. For the physical properties of the materials were studied, and it is revealed that the absorption spectra of the films are slightly redshifted in comparison with the solutions. This was due to intermolecular charge transfer properties in aggregate state or in solid state of the compounds, and the fluorescence spectra showed strong solvatochromic properties for fluorinated compounds in comparison with non-fluorinated. Quantum yields were studied and in tetrahydrofuran solutions as well as films, and it is revealed that the films displayed higher quantum yields in comparison with the solutions. This can be indicative of aggregation induced enhanced emission. In order to investigate further, we studied aggregation induced emission enhancement by dispersing the synthesized compounds in THF and water fractions, with water ranging from 0 to 95%, and for compound 3 at 60%, and for compound 1, 2 and 4 at 90%, we observed an increased intensity of emission due to the formation of aggregates, which in turn restricts intramolecular rotations. Photoelectron emission and charge transporting properties of the materials were studied, and it is revealed that for compounds 1 to 4, the ionization potentials are in the range of 5.8 to 6.4 electron volts, and time of flight measurements revealed that compound 1 displayed highest electron and hole mobilities at 10 power minus 3 square centimeters per volt seconds. Electroluminescent properties of the materials were studied by fabricating organic light emitting diodes, where the synthesized materials 1 to 4 were used as blue emitters, and compounds 3 and 4 with acridine moieties displayed highest external quantum efficiencies of 2%. The second series of materials is based on trifluoromethylphenyl moieties disubstituted for aromatic diamines. The target materials were synthesized in a single step Buchwald-Hartwig reaction, and the synthesized materials were used to investigate the thermal properties, and the 5% weight loss temperature in TD were in the range of 258 to 294 degrees Celsius, and differential scanning calorimetric analysis revealed that compounds 5 and 6 are crystalline in nature, revealing melting points at 180 and 170 degrees Celsius, and compounds 7 and 8 are amorphous in nature with glass transition temperatures at 74 and 54 degrees Celsius. The theoretical calculations of the second series of materials revealed that the highest occupied molecular orbitals of compounds are distributed over the molecular backbone of the materials, and lowest unoccupied molecular orbital of compounds 5 and 7 are localized to fluorine atoms, and however for compounds 6 and 8 they are distributed over the molecular backbone. And the single crystal analysis revealed that compound 5 displayed inter and intramolecular interactions with carbon to pi, carbon to fluorine and fluorine to hydrogen interactions. However, compound 6 with metasubstituted fluorine atoms displayed only inter and intramolecular interactions. Photophysical properties of the compounds were studied, and the absorption spectra revealed that for compounds 5 and 7 the films are slightly redshifted in comparison with compounds 6 and 8 due to the presence of naphthalene units, and the fluorescence spectra of the materials reveals strong solvatochromic properties for orthosubstituted materials in comparison with metasubstituted fluorine atoms, and the phosphorescence or singlet triplet energy was for compound 5 and 6 was observed lower in comparison with compound 7 and 8 with naphthalene units. The photoelectron emission and charge transporting properties of the materials were studied, and it is revealed that for compounds 5 to 8 the ionization potentials are in the range of 5.7 to 6.2 electron volts, and the time of flight measurements revealed that the hole mobilities for compounds 5 and 7 are 10 power minus 3 and 10 power minus 4 square centimeters per volt seconds. The third series of materials are composed of methoxy-substituted carbazole based monomers and polymers. The target materials 9 and 10, the monomers, were synthesized via Buchwald-Hartwig reaction. The polymers 11 and 12 were synthesized by polymerization using RAFT polymerization technique. The synthesized materials were used to study the thermal properties, and the 5% weight loss temperature for polymers 11 and 12 are 414 and 406 degrees Celsius, and the differential scanning calorimetric analysis revealed that compounds 9 and 10, which are monomers, displayed melting points at 72 and 62 degrees Celsius, revealing their crystalline in nature. However, compound 11 and 12 did not display any melting and rather displayed glass transition temperatures at 191 and 161 degrees Celsius, suggesting that they are amorphous in nature. The photophysical properties of the synthesized monomers and polymers were studied, and as we can see in the fluorescence spectra, the spectra of the solutions showed usual vibronic structures. However, the films showed slightly complex structure. This was attributed towards charge transport properties of the materials. However, the polymers do not have a typical donor acceptor type structure to produce a normal charge transfer. Hence, these shoulders were attributed towards the excimer emission, via excimer emission indicating through space charge transfer properties. The electroluminescent properties of the materials were studied by fabricating solution processable organic light emitting diodes, where the synthesized materials were used as hole transporting or host materials, and device D displayed highest external quantum efficiency of 10% which was composed of polymer 11. And the last series of materials are composed of 3 donor fragment materials, and it was the target materials are synthesized in multi-step reaction, and in the last step Buchwald-Hartwig was used to synthesize the target materials, and the thermal properties revealed that the weight loss temperature or TD in the range of 367 to 391 degrees Celsius, and the differential scanning calorimetric analysis revealed that compounds 13 to 16 are crystalline in nature, and compound 17 is amorphous in nature with 88 degrees Celsius of glass transition temperatures. The photophysical properties of the materials were studied, and we can see the absorption and emission spectra shows complex structure due to the charge transfer nature of the films materials, and the phosphorescence spectra of the materials were also studied, and the photoluminescence quantum yields for compounds 13 and 16 were higher in comparison with compounds 14, 15 and 17. The photoluminescence decay measurements of the materials were studied to investigate the lifetimes of the materials, and as we can see for compound 13 and 15 we saw lower lifetimes less than 100 nanoseconds. Compound 14 displayed room temperature phosphorescence, and compound 16 and 17 displayed longer lifetimes. This can be an indicator of thermally activated delayed fluorescence. To investigate further, compound 16 and 17 were used. Compound 16 and 17 doped with DPEPO were used to study the phosphorescence spectra and photoluminescence decay spectra, and it is revealed that in phosphorescence spectra the triplet energy is comparatively low in comparison with previously measured tetrahydrofuran solution measurements, and the photoluminescence decay spectra revealed that the longest lifetime of 159 microseconds for compound 17. Photoelectron emission and charge transporting properties of the materials were studied, and the ionization potential for the compounds are in the range of 5 to 5.6 electron volts, and the time of flight measurements revealed that compound 16 displayed highest electron and hole mobilities and 10 power minus 3 and 10 power minus 4 square centimeters per volt seconds. Electroluminescent properties of these materials were studied by fabricating red phosphorescent organic light emitting diodes, and the target materials were used in these devices, used as hosts in these devices, and device R3 with compound 16 as host displayed highest external quantum efficiency of 12.6%. Conclusions: in the first series of materials, 4 new target materials were synthesized successfully, and the target materials displayed highest electron and hole transporting capabilities, and the materials were used as blue emitters in organic light emitting diodes with 2% external quantum efficiencies. In the second series of materials, 4 new materials were synthesized successfully. The target materials showed strong mesomeric effect, and lower ionization potentials and enhanced hole mobilities were observed for these materials. In the third series of materials, the monomers and polymers were synthesized successfully. The target materials displayed through space charge transfer properties, and the synthesized materials were used as holes or hole transporting material for solution processable organic light emitting diodes. And in the fourth series of materials, the target materials were synthesized successfully, and the materials showed thermally activated delayed fluorescent properties and highest electrons and hole mobilities as well. The synthesized materials were used as hosts in red phosphorescent organic light emitting diodes. These are the list of publications that were related to the thesis. These are the list of scientific conferences that were attended during the PhD, and thank you for your attention.
Okay, thank you very much. You are very fast.
Thank you.
And but this is good, of course, property. Okay, according to the procedure of process, the dissertation defense is time for questions. So first of all, ask board members, but also from auditorium also can come questions. Please think about.
Yes, on slide number 4, you have demonstrated synthesis of the materials.
Okay, just a moment. Slide 4.
Yes.
Okay.
And the yield of the material 4 is very low as compared with some other derivatives in the group. So how you would comment the low yield of this compound?
The low yield for compound 4, well, we lost a lot of material while purification of the compounds from column chromatography as well as recrystallization. However, as you commented, it can be a possibility that compound 4 might also formed a secondary conformer like compound 2 with carbopalladiation, and there might be a loss of product over there as well, because there are two types of products that are forming. That can be a possibility, but we did not investigate on that, so I cannot be sure if that was primary reason for lower yields.
Okay. Okay, thank you. And one more question. On slide number 8, you demonstrate efficiencies of devices.
Yes.
So, and even for this kind of devices, the efficiencies are rather low. Would you have some suggestions how the efficiency could be improved or increased?
Okay, well, in this case, these are fluorescent type devices, and usually the EQEs for fluorescent type devices are limited to 5%, and at this point we can say that the efficiency of 2% was more or less reasonable, and the possibility to increase efficiency can be trying to use these materials as thermally activated delayed fluorescent type materials, because the compounds with fluorine atoms showed such possibility. So in that case we can try to increase the efficiency of the devices.
You mentioned thermally activated delayed fluorescence, but this group of material doesn't depend to this kind of material.
It is a possibility because the presence of fluorine atoms can be considered as electron withdrawing groups and donor acceptor type material, but we did not specifically study for that. We wanted to see if there was an increase in aggregation induced emission, hence this was focused on such type of devices only.
Okay, thank you for your answers.
Thank you.
Please switch on other participants. We need to see.
Okay.
Okay, and okay, there are no more questions from online members. You have.
I have a question about efficiency also, but it was answered already, but maybe I will ask about the second group of compounds. These compounds were not tested in OLEDs, so maybe you could predict what performance of these compounds could be if they were used in OLEDs.
Okay, for the second group of compounds, in this case we can see the ionization potentials and time of flight measurements, and the ionization potentials are reduced, and we see an increase in hole mobilities for compounds 5 and 7. This can be a good indicative that these materials can be used for hole transporting materials in OLEDs.
The glass transition temperature and melting temperature for all your compounds, because you have the same problems that you didn't explain it. So, in the firstly, for example, in your dissertation, you said first heating is mentioned, and there is no information about the second heating. Have you the second heating, and why you have the tissues, for example, is low, and then glass transition temperatures, and how you can obtain the same compound with different transition temperatures? Why? How you can explain this? And of course, this is about the 5 and 2nd compounds. You say that there is crystalline and the same. So you say that they have TGs, and of course in table you have TC. So what is about what thesis you are showing there?
Okay, perhaps the TC are the crystallization temperatures of the materials. So this was
how you explain this, and about what crystallization temperature you speak.
Okay. So in differential scanning calorimetric analysis, when we start to do the heating, in the first heating the compound melts at a certain temperature. In this case, we can see that the melting points are 28, 5 and 6, 28 and 26 melting points, 180 and 170 degrees Celsius. And at that point, we see the melting point and we start to cool down. And when you start to heat again in the cooling process, the melted compounds tend to recrystallize.
So of course you must write about this. If I read your dissertation there, and of course during your presentation also, you didn't speak about this. You only said that the compounds have this transition glass melting points or glass transition temperatures, and no information when you obtain these temperatures.
Yes, I'm sorry for the missing information.
And, the same is, please open the polymers temperatures.
Okay, yes.
Here also you have the same problem. You speak about the monomers, and then you say that the glass transition temperature is 151 about the monomers.
For the
I think surprising thing, so please explain this one.
Okay, thank you. So for the monomers, as we can see, both of them we have this active vinyl groups. At temperatures 76 and 62, they start to melt and even degrade. But also at those temperatures, due to the active regions of vinyl groups, they tend to self-polymerize. And what we are seeing, the glass transition temperature, are those self-polymerized polymers, which were from the monomers.
So you obtain it after when you cooling it?
Yes, yes, when it starts to change back during the cooling process. So once at those temperatures, the polymer has already formed. So
I think that you couldn't present as the glass transition temperatures of the monomers. You present them in the same for the compounds 9 and 10. So it is not the glass transition temperatures of the monomers. There are the glass transition temperatures of the polymers. You obtain simultaneously during the
process of
processes. How I think, I don't know how I understand how you can obtain glass transition temperature from these compounds.
Yeah, this was slightly.
He indicated in the table below
Yeah. Okay.
So this is all. The others are about the dissertation, which is not announced during the presentation. So I think I will ask.
Okay, I would like to ask, can you, because I'm not familiar with that synthesis method, maybe you can shortly explain how you perform synthesis of these materials. You just mixed some liquids or something like what are you? What is that?
Yes, so we take something called a donor type of material and then an acceptor type of material, and the primary reaction method used here was Buchholz-Hartwig, where a catalyst, a ligand and a base is used to combine these donor and acceptor types. For example, I can show you in the fourth series. Yeah. So technically it is an electron donating group in the core molecule. However, consider that depending on an electron withdrawing atoms, it can be an acceptor. So we use such method and try to construct or couple these two components by using the reaction procedure. It typically takes like about 18 to 24 hours, and then we purify it via column chromatography and recrystallization, and the structures usually are confirmed by NMR spectroscopy as well as single crystal analysis. So
Is there written synthesis temperature, for example?
no, here.
At which temperature you perform?
So such type of, in the last step where we used palladium, X-phos and tretbutyl, sodium butoxide. The temperature was between 110 to 115 degrees Celsius, which can be controlled by a heat, or
110 and
in the range of 110 to 120.
not necessarily very strict temperatures, can be some range.
It might vary during the reaction process itself. Sometimes it might go up, go down. We try to hold it at 110. It works for me here more or less. So.
If you will apply, for example, 500, not difference.
Okay, the pressure builds up and then more or less it will explode, but the heating plates won't even reach that temperature. The maximum we have are 250 degrees Celsius.
Okay, one question is about the aim of your work. And the aim is written as the first, is the design of compounds. In Lithuanian summary, it is more soundly written because it is written modelimus, understand? Modeling
Okay.
of compounds. But the modeling or design, it disappears in the past. Who you can explain? You performed design or modeling or not? And if yes, please explain.
Yes, the design in the synthesis part was a strategy to use aggregation-induced emission as well as thermally activated delayed fluorescence, and for polymers, in polymers case, through space charge transfer type of materials, and in the second series, more or less increased or enhanced hole mobilities. That was the design strategy or target which we wanted to acquire. Using that, we have certain type of materials which we can use to acquire this type of targets. So that was more or less design. But normally, in other words, design can be modeling, where we perform theoretical calculations for such materials, and then we acquire theoretical results, and based on that, then we strategize how to synthesize the materials, and then compare the theoretical results with the experimental results. That was also done for these materials as well.
You should simply say that you first draw those structures on the paper. This is the design.
Okay.
No, but you use some DFT calculations or something else?
Yes.
There are some results on that.
There are, but I gave specifically only for the second series of material, but for DFT calculations were performed for more or less all the series.
You did by yourself?
Yes, with the help of my supervisor, of course.
Please switch on again other team which is online.
Yeah.
Maybe there are more questions from participants online.
Yeah, we should ask us maybe
Professor Yashchuk, do you have questions?
There is such a result that redshift of spectra is attributed to charge transfer quantities. What is the origin of this charge transfer quantity? Maybe there is some possibility to charge transfer from one molecule to another. How do you think?
It is possible with inter as well as intramolecular charge transfer. However, the primary origin can be because of donor-acceptor type combination, which was observed for the fluorinated atoms. Due to the fluorines, they behave as donor-acceptor, hence giving us such charge transfer, intermolecular charge transfer. This can be the origin, Professor.
Well, the second question: what are the proofs that compounds 9, 12 manifest, namely excimer emission in the field? I mean, maybe a broad spectrum and absence of corresponding absorption, or no?
In this case, Professor, we do not have this typical donor-acceptor type materials to produce that charge transfer. So this charge transfer can be assigned due to the formation of excimers, and the excimers, like these are the complexes formed during the excited as well as the ground state materials. And the charge transfer occurred between those materials which are in close proximity. Hence, we can prove that this is an excimer type of emission with charge transfer occurring through space without a chemical carbon-carbon bonding or a chemical bonding.
Well, the question 2 or 3. Confusion in confusion. Confusion 1 little a.
Conclusion.
Do you see it?
Oh yeah. Okay. 1A.
What is the reason of aggregation-induced emission enhancement?
Yes. In general case, when the
perhaps this is connected with non-functional difficulties in the internal movement of molecules in aggregates, or no?
yeah, well, in aggregate state where you have
some difficulty in moving. I mean, space difficulty.
okay. In this situation, Professor,
How do you think?
the formation of aggregation-induced emission, correct? So the charge transfer, okay, in aggregate state, the materials are closely packed, and the fluorine atoms kind of help us in planarization of such molecular packing, and this helps in efficient charge transfer within the molecule as well as externally from the molecule, giving us increased intensity of emission. That's the primary. Yes.
Very nice.
Thank you.
So that's all my questions.
Okay, thank you very much for questions.
Three my questions.
Yeah, you can finish.
Okay.
Okay.
Okay, thank you. More questions from auditorium, maybe?
Maybe I continue only with the question you say about the enhanced fluorescence, but how I see you have also the color change. how you can explain the color change during this aggregation?
The red shift or blue shift, it more or less depends on the polarity of the environment in which we use. In this case, when water was increased, the polar solvent concentration was reduced. This kind of helps in shift of the spectra towards red.
Not in our cases, because for the first case,
Again, our team members, maybe they still have questions. No more questions from online participants now. From auditorium, Julia.
Possible, yeah. There was a lot of talk about the impact of aggregation on the properties, and you also use PhD. In your experience, what do you think? Is it possible to adequately predict aggregation properties by using theoretical methods, or do you have to do only experimentally? What do you think about this?
Okay, good question. All right. So we can predict by using differential calculations. However, the experimental results may not be as predicted. So the accuracy more or less depends on the experimental results. So we can theoretically say that it can produce a type of aggregation induced emission, but the intensities, such things can be only via experimental process.
Okay. More questions? Okay, we finish question session, and according to procedure, we go to now is I need to provide with opportunity to speak supervisor and advisor. Now I ask to talk a little at the supervisor, Dr. Andrulevich.
So during his Bernard's PhD studies, he obtained some quite interesting results, and these results were successfully published. Bernard worked a lot in the laboratory on the synthesis. Also, he had a very good relationship with the group members. He is ambitious. As I know, he is planning to continue more in the field of scientific research. So I wish you good luck
Thank you.
in your future plans.
Thank you.
Okay, thank you. And maybe somebody have question to supervisor? No. We will ask second supervisor and also advisor, Professor Andrulevich.
My wishes are similar to the advisor. The main merit of Bernard is that he gets very good social skills. So these social skills help him in his research, because his background when he arrived, he made his bachelor degree in quite different fields, so he needs the support from the group members, and these social skills help him. So, to my opinion, he would be very good manager. He even we see from his dress that he could be very good manager. Yeah, but he likes research, and as far as I know, he will proceed his research at Vilnius University.
Okay, thank you.
Good luck.
Thank you, Professor.
Thank you. And now is